On a computer network, every endpoint uses a unique IP address. Applications that provide communication between endpoints use these addresses to identify communicating end devices. If you want to access a resource available on an endpoint, you have to use its IP address. For example, if you want to access a website stored on a server, you have to use the server's IP address. Generally, IP addresses are difficult for human to remember. IP addresses are made of numbers. Instead of numbers, humans prefer names to identify and access objects on the network. Let's take a simple example. Suppose you want to access Google's website. Google's website's address is available in three formats: IPv4, IPv6, and name. Which format will you use on the browser to access Google's website? Most of us will use the name rather than the IPv4 and IPv6 formats. It is more convenient and easier to use, speak and type. But there is a problem: computers never use names to access any resources available on the network. The solution to this problem is mapping. Computers allow us to map IP addresses with their respective names. After mapping, when we access a resource by using its name, the computer automatically converts the name into the IP address. There are two ways to map IP addresses with names: using the host's files and using the DNS server. Let's understand both methods. All operating systems include a file called hosts. You can use this file to map IP addresses and names. Each time you access a network resource, the operating system checks this file to find the corresponding IP address. Let's understand this through an example. In this video, I will use the virtual lab I have set up to practice RHCE exam topics. To learn how to set up this lab, you can check this video. The link to this video is available in the description. Since we are not allowed to use the internet during the exam, I didn't configure the virtual systems to use the host's internet connection. If you have set up the same virtual lab for practice, you also need to configure one virtual system to access the host's internet to complete the exercises explained in this video. To do this without messing with the existing setup, you can add a new LAN card and configure it as a bridge connection. A bridge connection allows the virtual machine to access the host's internet connection. After doing all exercises explained in this video, you can remove this LAN card. Now power on this virtual machine. Log in from the root account. Linux saves the host's file in the /etc directory. By default, this file has only two entries. Both entries map the name localhost to the loopback address. To verify it, let's open a terminal and view this file. To view this file, we can use the cat command. As we can see here, this file has only two entries and both entries map the name localhost to the loopback address. This file stores entries in lines. Each line represents a single entry. Each entry includes two things: an IP address and a name. The IP address is written first. The related name is written after a tab space. Localhost is the default hostname on Linux. If you don't configure a hostname or delete all configured hostnames, Linux uses this name as the default hostname. To know more about the hostnames, you can check this video. This video explains everything you should know about hostnames on Linux. A loopback address is a reserved IP address. It is used to check the TCP/IP protocol suite on the local system. If you get a reply from this address, it verifies that the TCP/IP protocol is working fine on the local system. There are two versions of IP addresses: IPv4 and IPv6. In IPv4, the IP address 127.0.0.1 is reserved for the loopback address. In IPv6, the IP address 1 is reserved for the loopback address. When we access a network resource by using its name, Linux first checks this file to find its IP address. If it finds the corresponding IP address in this file, it uses that IP address to access the resource. To verify it, open the web browser and access Google's website. Linux first checks the host's file to know which IP address is associated with the name google.com. If it does not find an entry in this file, it checks the DNS server to find the IP address associated with the name google.com. The DNS server finds the IP address associated with the name google.com and shares that IP address with the system. The system uses the shared IP address to access Google's website. If the system finds Google's IP address in the host's file, it does not check the DNS server for it. Right now, the host's file has no entry for the name google.com. Because of this, the browser will use the DNS server to find the IP address associated with the name google.com. The DNS server will find and share the IP address associated with the name google.com. To verify it, let's open this file. As we know, we have two versions of IP addresses, IPv4 and IPv6. Let's add two entries for the name google.com, one for each version. This entry will map the name google.com with the loopback address on IPv4, and this entry will map the name with the loopback address on IPv6. Now when we will access Google's website, the browser will check this file to know the IP address of Google's website. This file tells the browser that the IP address of Google's website is 127.0.0.1 on IPv4 and 1 on IPv6. The browser tries to load Google's website from these addresses. Since these addresses belong to the local system and the local system does not have Google's website, the browser fails to load Google's website. We mapped only the name google.com with the loopback address. We didn't map any other website's name. Because of this, the browser will use the DNS server to resolve the name of other websites. The DNS server will tell the actual IP address of each website to the browser. Because of this, you will be able to access other websites. As you can see here, we can access other websites, but we can't access Google's website. It verifies that the system uses the host's file to resolve a name in the first place. If it does not find an entry in the host's file for a name, only then it sends a query to the DNS server to find the corresponding IP address of that name. Now, open the host's file again. Remove the entries that we added here. Save the file. Use the cat command to verify the change. As we can see here, the entries that were mapping the name google.com with loopback addresses have gone. Now access Google's website again. As you can see here, now we can access Google's website again. At this time, the host's file does not have an entry for Google's website. Since the host's file does not have an entry for Google's website, the browser uses the DNS server to resolve the name google.com. The DNS server tells the actual IP address of google.com to the browser, and the browser accesses the website. If you have a small size network or want to access only some services from the network, you can use the host's file for the name resolution. But if you have a medium or large size network or want to access multiple services from the network, you cannot use the host's file for the name resolution. Let's take an example to understand it. Suppose you have a small network of 5 computers. Computers do not access any service from the internet or external networks. They access only the resources available inside the network. Since computers do not access anything from external networks, you can configure and use the host's file on each computer. You need to create and manage only 4 records in each host's file. If the IP address or name of a computer changes, you need to manually update the host's files on all computers to reflect the change. Managing a few files or records is simple and possible. But if you have a medium or large size network, you have to create and manage thousands of records in the host's file of each system. That is a tough task. You have to spend most of your time in managing these files or records. If you access the internet, the situation becomes worse. There are millions of websites on the internet. You need to create a record for each website in the host's file of each system. If the IP address of any website changes, you need to manually update the host's files on all computers to reflect the change. That is a practically impossible task. The solution to this problem is to deploy a dedicated computer for the name resolution service on the network. The dedicated computer will perform only one task, that is resolving names with IP addresses. Since it will resolve names with IP addresses, we can call it a resolver computer. In simple words, a resolver computer is a computer that resolves names with IP addresses on the network at the fastest possible speed. It can be a DNS server or a system that is configured to communicate with DNS servers to resolve IP addresses. Based on the size and requirement, a network can have a single or multiple DNS servers. For example, the Internet, the largest computer network, uses thousands of DNS servers. If a network has only one DNS server and does not use external DNS servers, the role of the resolver system and the DNS server is the same. In this situation, network computers can directly communicate with the DNS server for name resolution. Since the DNS server directly resolves queries, it also works as a resolver system. If a network has multiple DNS servers or uses external DNS servers, the role of the resolver system and the DNS server is different. In this situation, network computers do not directly communicate with DNS servers for name resolution. They send queries to the resolver system and the resolver system communicates with DNS servers to solve queries. In a network, a resolver computer performs the following tasks. Let's understand these tasks in detail. It removes the burden of managing records in the host's file from other computers. Once a resolver system is configured, other computers of the network do not need to maintain records in their host's files. It reduces the number of DNS servers' IP addresses you need to configure on each network system. Suppose your network uses multiple DNS servers. Without a resolver system, you need to configure the IP address of all DNS servers on all computers. But with the resolver system, you only need to configure the resolver system's IP address on each computer. It improves the network's performance and efficiency. If the resolver system is configured, only the resolver computer communicates with DNS servers. Other computers don't need to use their hardware resources to communicate with DNS servers to resolve queries. Let's take an example to understand how this process works. Suppose a system wants to know the IP address of google.com. For this, it first checks the host's file. If it finds an entry associated with the name google.com, it uses the IP address mentioned in the entry to access google.com. If it doesn't find an entry in the host's file, it checks the file that stores the IP address of the resolver system. Linux stores the IP address of the resolver system in the /etc/resolv.conf file. If this file has the IP address of the resolver system, it creates a query to know the IP address associated with the name google.com and sends that query to the resolver system. If the resolver system is a DNS server, it checks its database, finds the IP address associated with the name google.com, creates a reply message that includes the IP address associated with the name google.com, and sends that message back to the system which sent the query message. If the resolver system is not a DNS server, then it forwards the query to all configured DNS servers in a sequence until it gets the IP address of the name it is looking for. Once it gets the IP address of the name, it does not send the query to the next DNS server for that name. Usually, resolver systems are also configured to cache the result. If caching is enabled, the resolver system saves a copy of all replies it receives from DNS servers. Next time, if it receives a query for the same name, instead of forwarding the query to DNS servers, it uses locally saved copies to answer the query. The sender system learns the IP address of google.com from the reply message it receives from the resolver system. Just like DNS servers, you can configure multiple resolver systems on the network. Network computers check them in the defined sequence until they get the answer to their queries. Once they get the answer, they don't send the same query to the next resolver system. It allows you to deploy multiple resolver systems as a backup in a sequence. Let's take an example. Suppose you have two resolver systems. IP addresses of these systems are 10.0.0.1 and 2. You want to use the first resolver system as the main resolver system and the second resolver system as the backup resolver system. For this, you need to configure the IP address of the first resolver system on network computers as the primary resolver system and the IP address of the second resolver system as the secondary resolver system. Network computers will use the primary resolver system to resolve queries. If the primary resolver computer fails or loses connectivity, they will use the secondary resolver system to resolve their queries. Linux saves the resolver system's IP address in the /etc/resolv.conf file. It uses the name server directive to save the resolver system's IP address. If multiple resolver systems are configured, it will save their IP addresses in the sequence. In this sequence, the first IP address belongs to the primary resolver system. The second IP address belongs to the secondary resolver system, and so on. You can edit or update these IP addresses in two ways, by using Network Manager's tools or by directly editing this file. Let's understand both methods in detail. Red Hat Linux uses Network Manager as the default daemon process for managing and configuring all networking related settings. Network Manager provides three tools to configure network settings. These tools are nmcli, nmtui, and nm Connection Editor. nmcli is the command line tool to manage network connections. nmtui is the curses-based utility. You can use it on both CLI and desktop. nm Connection Editor is a desktop utility. You can use it only on the desktop environment. You can use any one tool from these tools to configure or change network settings. Let's use nmtui utility to edit a connection. Select the connection you want to edit. At this time, this connection is configured to get IP configuration from the DHCP server. To manually configure the DNS server's IP address, first, we have to change the configuration type to manual. Now we can manually assign an IP configuration to this connection. We can't use a connection without an IP address. Let's assign an IP address first. Now we can configure the DNS server or resolver system's IP address. Let's assign an IP address. Since it is the first IP address, it will work as the primary DNS server or the resolver system. As I have already mentioned, a resolver system can be a DNS server or a system that is configured to communicate with configured DNS servers. If it is a DNS server, it will resolve the query from its database. If it is configured to communicate with DNS servers, it will forward the query to all configured DNS servers in a sequence until it finds the answer. If you want to configure the secondary DNS server or resolver system's IP address, you can use the Add option. Let's assign one more IP address here. It will be the IP address of the primary DNS server or resolver system. It will be the IP address of the secondary DNS server or resolver system. Save the configuration. Use the back button to access the main screen. Network Manager saves the configuration in the file, but it does not apply changes to the active connection. To apply changes, we need to restart the connection. For this, select the second option. Select the connection you want to restart, deactivate the active connection, and activate it again. Quit the tool. Network Manager saves each connection setting in a configuration file in the /etc/sysconfig/network script directory. It uses the connection name as the file name after the ifcfg prefix. For example, we edited the connection named wired connection 1. The name of its configuration file will be ifcfg wired connection 1. Let's check this file. This is the IP configuration we assigned to this connection. These are the DNS servers or resolver systems IP addresses. This is the IP address of the first or primary DNS server. This is the IP address of the secondary DNS server. When we activate or reactivate the connection, Network Manager pushes these IP addresses in the resolv.conf file. To verify it, let's check the resolv.conf file again. As you can see here, this file has been updated to use the DNS servers or resolver systems we configured recently. Linux dynamically updates this file from the network configuration. Because Linux dynamically updates this file from the network configuration, you should not update this file directly. If you directly update this file, your changes will be overwritten the next time when you will activate or reactivate a connection. To understand it practically, let's edit this file and configure the resolver system's IP address manually. Replace these IP addresses with any other IP addresses. Save the file. Use the cat command to verify the changes. As we can see here, the resolv.conf file has been updated successfully. Right now, it is pointing to manually updated DNS servers. But it will do this only until we don't reactivate a connection. As soon as we will reactivate or activate a connection, it will be overwritten again to point to the named servers configured in the connection. To verify it, let's reactivate the connection we recently configured. To reactivate the connection, you can use the nmtui utility again. After reactivating the connection, check the resolv.conf file again. As you can see here, this file has been overwritten again to point to the DNS servers configured in the connection. Because of this, you should always use Network Manager's tools to update the DNS servers or resolver systems IP addresses. The /etc/nsswitch.conf file defines the default order for services that use multiple sources to get information. For example, the resolver service uses the hosts file and resolver systems to get the IP address of a name. Which source it uses first is defined in this file. If the service uses both sources, this file defines the order in which the service uses them. This line defines the default source order for the resolver service. As we can see here, it uses two sources, files and DNS. The option files denotes the hosts file. The option DNS denotes the resolver system. The resolver service processes this order from left to right. To resolve a name or an IP address, it first checks the hosts file. If it finds the answer in the hosts file, it does not check the resolver system. It checks the resolver system for the name resolution only if it doesn't get the answer from the hosts file. Let's understand it through an example. Check the /etc/hosts and the /etc/resolv.conf files. By default, the hosts file has only one entry for the name localhost. Localhost is the default name for the local system. If you don't configure or remove all configured host names from the local system, the local system uses this name as the default host name. The resolv.conf file saves a list of DNS servers or resolver systems IP addresses. If the resolver service does not find an entry for a name or an IP address in the hosts file, it sends a query to all configured DNS servers or resolver systems in a sequence until it finds the answer. This order is defined in the /etc/nsswitch.conf file. To understand how this order works, let's open the browser and access Google's website. The browser checks the /etc/hosts file to find the IP address associated with the name google.com. Since the hosts file does not have an entry for the name google.com, it checks the /etc/resolv.conf file to find the resolver system's IP address. If the resolver system's IP address is configured in this file, it creates a name resolution query and sends it to the resolver system. The resolver system finds the IP address associated with the name google.com and shares that IP address with the requester system. This is the default order the resolver service follows on the local system for the name resolution. If you want to change this order or modify the action the resolver service should take at any source in the sequence, you need to update the nsswitch.conf file. You have 4 options to change the default action it takes at every source in the sequence. These options are success, not found, unavailable, and try again. You have 2 values for these options. These values are return and continue. Let's understand the meanings of these options. The first option is success. The default value of this option is the return. This option with the default value says if the resolver service finds the information it is looking for from the source, it should not check the next source. The second option is not found. The default value of this option is continue. This option with the default value says if the resolver service does not find the information it is looking for from the source, it should check the next available source in the sequence. The third option is unavailable. The default value of this option is continue. This option with default value says if the source is down or not available, the resolver service should check the next available source in the sequence. The fourth option is try again. The default value of this option is continue. This option with default value says if the source is too busy or unable to answer the query, the resolver service should check the next available source in the sequence. Let's take an example to understand how to use these options to modify the default behavior. Open a new terminal. Since this file controls the default order of many services, you should always take a backup of this file before modifying or updating it. If you have a backup copy, you can restore the original file from it in case anything goes wrong. Now let's open the file. Go to the line that controls the default order for the resolver service. Here the host's file is defined as the first source. Because of this, the resolver service first checks the host's file. If it finds the entry for a name in the host's file, it does not check the resolver system for that name. If it does not find the entry for a name in the host's file, it checks the next source for that name. Here the next source is the resolver system. Now suppose we want to modify the default behavior at the first source. We want that the resolver service does not check the next source if it does not find the answer in the host's file. The second option defines the default action the resolver service takes if it does not find the answer in the source. The default value of this option is continue, which allows the resolver service to check the next source in the sequence. If we change this value to return, the resolver service will not check the next source if it does not find the answer in the source. Let's change the default value of the second option and save the file. Verify the change. As we can see here, the default action of the not found option has been changed. Restart the browser. Now access the internet again. As you can see here, now we cannot access the internet. To access the internet, the resolver service needs to access the resolver system. With the current configuration, the resolver service can't access the resolver system. It can access only the host's file. If the host's file does not have information about a name, it is not allowed to check the next source. The resolver system is the next source. The resolver service can access it only if the default action of the not found option is set to continue. Let's remove the custom value of the second option. For this, you can edit the file again or can restore the original file from the backup. To use the default value of an option, you don't need to specify the option. By default, the resolver service uses the default value of each option. Now restart the browser and access the internet again. As you can see here, now we can access the internet again. It verifies that the resolver service follows the order specified in the nsswitch.conf file. By using this file, you can customize the order the resolver service uses for the name resolution. That's all for this video. If you have any comments, suggestions, or feedback about this video, please share them in the comment section given below.